Have you ever wondered what goes on behind the scenes of building and improving an e-commerce platform? Well, you're in the right place. Today, we are pulling back the curtain to reveal the trials and triumphs of developing our e-commerce system. This journey isn't just about technology, it's about the people, decisions, and strategies that drive success in the fast-paced world of online shopping. As we unfold this story, we'll begin by diving into the original architecture, highlighting the specific issues we encountered in production. We'll then discuss various potential improvements, weighing their advantages and disadvantages, and explore different paths a project could have taken. Through collaboration with our product owner and aligning with our business's vision, we made crucial decisions that shaped our platform's evolution. Key figures in this story include Luka, the leader of the payment team, Nina, the product owner, and myself, Pop, the architect behind the scenes. Now, without further ado, let's dive into our story and uncover how we navigated through all these challenges. I'm quietly working in my office, updating our Confluence documentation, when Luka bursts in. His face is flushed, he's breathing heavily, and he exclaims, "Pop, I can't take it no more. My team works tirelessly to implement new features and meet business requirements, but the system is crumbling. I barely slept last night. Black Friday is a nightmare. We had so many requests flooding the platform that it was on the verge of collapse." Whoa, that sounds rough. Were you able to find a way to stabilize things and get the system some breathing room? I did what I had to. I couldn't code on the spot, but I wasn't about to let things fall apart. I made some emergency tweaks, increased those database timeout values temporarily, combed through Postgres Activity Monitor, and killed all those non-essential long-running queries that were holding locks on critical resources. This buys us time, but you know it's not a long-term fix. We've got to make some serious changes here. You made smart calls under pressure. Now, this puts a fire under our re-architecting plans. Did you notice any patterns in the queries causing those logs? Are we hitting limitations of our current database schema? How about we sketch out the system and database on your board? Talking it through visually might give us some fresh ideas on where to optimize. Great idea! I will get us started and you can jump in with your insights whenever you're ready. Alright, let's break the architecture down from the very beginning. Traffic enters our system through two main clients. The web browser and the mobile app. These are the front lines of user interaction, whether it's someone shopping on their laptop or using the mobile app on the go. All requests from these clients flow into our backend infrastructure. Now the first stop for this traffic is our layer 4 load balancer. Think of it as the system's traffic cop. It works at the network layer to manage the flow of incoming requests, deciding which API gateway instance should handle each one. This decision is based on low-level information such as IP addresses and ports, making it lightning fast. Importantly, the L4 load balancer also serves as a first layer of protection, filtering out bad traffic like potential DDoS attacks before they even reach the core of our system. Now, once the request makes it through L4, it hits the API gateway. This is the brains of the operation. It manages all the heavy-duty work, authentication, rate limiting, and making sure only the valid requests pass through. The gateway centralizes security and routes traffic to the right backend service. Plus, it adds caching to speed up response times. After the API gateway, we've got our layer 7 load balancer. This one's more sophisticated than L4, making decisions based on the content of the request, like the URL, headers, or cookies. It also uses a consistent hashing algorithm to ensure requests from the same user or session are routed to the same backend instance. This helps us direct traffic to the right service, whether it's payments, orders, or inventory, more intelligently, improving performance and consistency. Yeah, I get it, but man, this setup is complex. Look at all these layers. L4, API gateway, L7. It's powerful, but it's also costly to maintain. The infrastructure costs add up. Is it really worth all this? Feels like overkill just to handle traffic spikes like Black Friday. You're right, it's not cheap, and it's definitely more complex than other options. But here's the thing, this setup has served us well for the last 2 years. Remember last Black Friday, when we scaled up and handled millions of requests without a hitch? It's this exact architecture that gave us the capacity to grow without falling apart during surges. Sure, it's an investment, but the flexibility and stability it brings are critical, especially when traffic spikes. So let's build on what we have and identify bottlenecks where they really matter. Alright, Luka, let's talk about why we went with the AWS. Cognito. For authentication, there are a few key reasons behind our decision. First off, scalability. Cognito handles traffic surges effortlessly, whether it's a typical day or a Black Friday madness. We don't need to worry about the authentication layer buckling under pressure. It just scales automatically with our needs. Then there is security. We knew we couldn't cut corners here. Cognito comes with strong features like multi-factor authentication built in. It's critical for protecting our users' sensitive information. It keeps our platform secure without us needing to implement complex solutions ourselves. Another big reason, we are already heavily invested in AWS. Most of our services run on AWS. So integrating Cognito was a natural fit. It works seamlessly with everything else. And let's not forget, one more reason: user experience. With Cognito, our customers can log in using their social credentials. Google, Facebook, you name it. It simplifies the login process for them, and for us, it means fewer barriers to entry. The easier it is for users to sign up and log in, the better it is for our business. Well, that makes sense. Less friction for the users and more time for us to focus on what matters. Here's why we need the user service. Cognito is great for handling authentication. It gives us a unique user ID to identify each customer. But for everything beyond that, like storing preferences, managing shopping history, and securely handling payment methods, Cognito falls short. That's where the user service comes in. It takes care of all the extended user data we need for personalization and ensures we stay compliant with regulations like GDPR. Each service, like order or cart, only stores the user ID locally and fetches extra data from the user service when needed. This keeps our services independent and the system fast, even under heavy traffic. Plus, this setup is flexible, so if we need to add new user features later, we just update the user service without touching everything else. And of course, sensitive data stays secure within the user service, ensuring we are handling security and compliance properly. That makes a lot of sense. So we are basically offloading all the heavy user data to the user service, keeping each part of the system lean and fast. And with the user ID being the key across services, we are avoiding unnecessary dependencies. Plus, knowing sensitive data like payment info stays secure and compliant with GDPR puts my mind at ease. Sounds like we've got a solid foundation to build on without risking any bottlenecks when traffic spikes. Now let's dive into product management and search strategy. Here's where the things get interesting. We've implemented a separate product CMS service and a search service. Two components that work closely together but handle entirely different responsibilities. The CMS service is where product data lives and breathes. It allows non-technical users like product managers to easily update and manage our entire product catalog. You know how quickly things change in our product database. New products, promotions, detailed specs, all of that needs to be kept up to date in real time. Right, and it makes sense to have a dedicated service just for that, so we are not crowding our search system with data management. Exactly, it keeps things streamlined. Now as for the search service, this is where Elasticsearch comes in. It's optimized for blazing fast search queries. Now every time we update product data in the CMS, we publish those changes through Kafka, which acts as a message broker. This way, the search service can update its indexes without any direct dependency on the CMS service. By decoupling these services, we allow each to scale independently. So when the business pushes out a big marketing campaign, the search service can handle the surge in traffic, and the CMS doesn't get overwhelmed. Plus, by relying on Elasticsearch for search queries, users can find products quickly, even under heavy load. Okay, so this means our search results are always up to date, but we are not overloading the product database every time someone runs a query. Exactly, and the best part, Kafka ensures any data changes are reflected asynchronously, meaning our system stays responsive even when we are handling a ton of data behind the scenes. Let's dig a little deeper into how the search service actually works. As I mentioned, Elasticsearch plays a key role here, but the magic is in how it interacts with the data. You see, instead of querying the product database for every single search request, which would slow things down, Elasticsearch handles most of the heavy lifting. When user searches for a product, we are not hitting the product database. Instead, all the relevant product attributes, name, price, category, brand, color, and others, are already indexed in Elasticsearch. This makes the search lightning fast, even if there are thousands of products. Got it! So we are avoiding a direct hit on the database every time someone types in a search query. Exactly, and here's where the things get really interesting. For most searches, Elasticsearch has everything it needs in its indexes, but some products have special attributes, like custom features or configurations that aren't part of the core product attributes. These special attributes are handled separately using the entity attribute value model. The entity attribute value model allows us to store these dynamic attributes without overwhelming the main product table. Instead of adding more columns to the product table for every new attribute, we store them in a separate table, where each new attribute is a new record. This keeps the main product table lean and efficient. These special attributes are not indexed in Elasticsearch, which focuses on the core attributes. When a search involves these dynamic attributes, they are fetched directly from the product database. So Elasticsearch is doing the heavy lifting most of the time. But the problem is when it doesn't have all the attributes indexed. We are relying on the product database to fill those gaps. We call the product CMS service synchronously to fetch those attributes from the database. And that's where the things start to fall apart during high traffic events. Exactly. We've been offloading the most commonly queried attributes, like product name, price, and category, which are part of the product table, to Elasticsearch to reduce the load on the product database. But the entity attribute value model introduces complexity. When those dynamic attributes aren't indexed, the database has to pick up the slack, and that's creating a bottleneck under load. Right, so we are efficient most of the time. But as soon as someone queries those specific attributes, it's game over for performance. We need to fix that gap, or we'll keep running into the same issues during peak traffic. Exactly. We need to either expand what we index in Elasticsearch or find a better way to manage those database hits. At least we've pinpointed one of the issues here. Let's mark this down for deeper exploration later, once we've got the full picture. Yeah, good call. We can tackle this more thoroughly later. Let's continue mapping out the architecture so we can identify any other weak points. Alright, Luka, let's break down the payment flow and see how everything connects. First up is the cart. Service. This service manages everything related to the user shopping cart, adding items, removing them, adjusting quantities. Its main job is to keep track of what the user wants to buy. But when the user checks out, the cart service doesn't handle payments or inventory directly. Instead, it sends a checked out event to kick off the rest of the process. So the cart service publishes a checked out event to Kafka, and this event is picked up by the order service. Now the order service is where the order lifecycle really begins. It handles order validation, inventory checks, payment processing, and tracking of the order status as it goes through different stages. When an order is created, the order service checks with the inventory service to confirm that the items are actually available. This step is crucial because we don't want to let a customer place an order if we don't have the stock. The inventory service keeps track of product quantities, updates the stock levels, and can reserve inventory for orders temporarily. And if inventory isn't sufficient, the order is cancelled immediately. We are not waiting around to confirm the payment. Exactly. If the inventory service says we are out of stock, the order service cancels the order right away, sending an order cancel event back through Kafka. But assuming inventory is good, the order service moves on to the next step. Next is the payment. Service. Its main responsibility is to process payments securely and reliably. This service doesn't just handle basic payments. It also manages retries and any necessary payment validations, like fraud checks. When the order service sends an order created event through Kafka, the payment service picks it up and tries to process the payment. Here's where Stripe comes in. The payment service makes a synchronous API call to Stripe to handle the actual payment processing. We need this call to be synchronous because we can't complete the order until we know for sure whether the payment went through or not. Exactly! The synchronous call ensures immediate feedback on payment status. And in case of payment failures, the payment service publishes a payment failed event for the order service to act on. Right. And if the payment fails, the order service cancels the order, releasing any reserved stock and returning the item to the card. Plus, the notification service also sends an alert to the customer to let them know the payment didn't go through. Now, if the payment is successful, the payment service sends a payment succeeded event. The order service finalizes the order, and everything moves forward from there. Throughout this process, each service is focused on its specific role, which keeps the architecture modular. Precisely, Kafka keeps our services loosely coupled, and it gives us event-based tracking at each stage. Exactly. Kafka allows us to handle communication asynchronously, making the system more resilient and scalable. If one service goes down, the others can continue working. And when the offline service comes back up, it can pick up where it left off. With this saga pattern, each service handles its own part of the transaction. If a payment fails, the order service rolls back the order and releases inventory without holding up the system. Exactly. Compensating actions prevent bottlenecks like locking inventory or delaying orders, keeping the system efficient. All right, Luka. Let's talk about the wish. List. Service. The wishlist service allows users to save items they are interested in for later. It bridges casual browsing and committing to a purchase, making it easy for customers to track products they like without cluttering their cart. It's not just about convenience, it's about encouraging users to stay engaged and return to complete their purchases. When a user adds an item to their wish list, it's stored in the wishlist service database with a default status of available. But the real action begins when a user moves an item from their wishlist to the cart. The wishlist service performs a synchronous inventory check to confirm the item is in stock. If the item is available, it makes another synchronous call to the cart service to add the item to the cart. And then the item status in the wishlist service database, it's updated to in cart, indicating it's in the process of being purchased. That makes sense. This way users get immediate feedback if the item is out of stock. they know right away instead of being left in the dark. Exactly. It's all about building confidence. Customers want to trust that the items in their cart are actually available. But it does not stop there. The wishlist service subscribes to Kafka topics to listen for order updates. If the purchase is successful, the wishlist service deletes the item from the wishlist database. If the purchase fails, like due to a payment error, the item status is reset to available, keeping it in the wishlist for the user to try again. That's a nice touch. It ensures users don't lose track of items they wanted, even if something goes wrong during checkout. Exactly. This hybrid approach combines synchronous calls for immediate feedback with asynchronous events for non-critical updates. It ensures seamless transitions, balances speed and scalability, and keeps the user experience consistent, even during high traffic events. Alright, let's break down the review. Service. This service ensures users can post reviews only for products they've actually purchased, boosting trust and authenticity. Right, that's why the microservice interacts with the order service to verify purchases before accepting reviews. It ensures only verified buyers contribute, which is crucial for maintaining credibility. Alright, let's break down the architecture of our new recommendation system. The core idea is to divide responsibilities between two services, the recommendation generation service and the recommendation. Delivery. Service. This separation ensures scalability and keeps each service focused on its specific task. The generation service gathers data from multiple sources. The user service, product CMS, search, cart, order, wishlist, and the review services. It processes this data to build models that predict user preferences using machine learning algorithms. These models are then used to generate personalized recommendations, which are stored in Amazon Key Spaces, our choice for a managed Cassandra solution. Right, Cassandra, and by extension Key Spaces, is a strong fit here, because it handles high throughput writes and reads efficiently. plus its structured schema model let us optimize access patterns for machine learning outputs, like retrieving recommendations for specific users or popular categories. Exactly, the defined structure in Cassandra makes it easier to query the data quickly and in predictable ways, which is crucial when machine learning generates large volumes of recommendation data. For the machine learning part, we are scheduling jobs to periodically retrain models using aggregated data. Meanwhile, real-time user behavior, streamed through Kafka, dynamically adjusts individual recommendations without requiring a full model retraining. This ensures our recommendations stay relevant, reflecting the latest trends and user actions, while keeping long-term model accuracy high. Once the models generate updated recommendations, the generation service pushes them to the delivery service by publishing recommendation-generated events. The delivery service then stores them in Redis for fast retrieval, ensuring users retrieve recommendations with minimal latency, without needing to query key spaces in real time. Redis acts as a caching layer, keeping the system efficient and responsive. Redis is perfect for real-time delivery. By caching recommendations with both time-to-live expiration rules and Kafka-driven updates, we ensure that users always see fresh suggestions without making expensive queries to the data store. Kafka keeps Redis updated asynchronously whenever new recommendations are generated, while time-to-live ensures that stale recommendations are automatically removed if no updates arrive for a while. This way, we prevent serving outdated suggestions and avoid storing unnecessary data indefinitely. Another important piece is scalability. By decoupling the generation and delivery services, we can scale them independently. If we see a surge in user activity, we scale the delivery service. If data processing demands increase, we scale the generation service. This architecture ensures we are always responsive. And by decoupling generation from delivery, we've simplified maintenance too. Updates to the recommendation models won't disrupt the delivery pipeline. And that brings us to the end of our architecture deep dive. We've laid out how our e-commerce platform handles traffic, processes orders, and manages search and recommendations. But even the most well-structured system has its breaking points. In the next video, we will shift gears to uncover the biggest challenges: inventory bottlenecks, database strain, and search inefficiencies, and explore different paths forward where technical decisions meet business realities. See you in part 2!